will give you more information later.
That's the same thing. They probably won't give you anything until.
In fact, I'm so far from failing.
As long as I get something.
Tried to keep the only thing I've heard back from.
Wow, oh, sorry. It worked out, but
It was quite a surprise. It was a surprise to me that it traveled. Okay.
Will do.
I don't need an A either.
Did
But I
you
don't
get
want
the
to
email?
Unless it's like somehow clutch.
They haven't called you, then you probably have 8 stars.
That's real, yeah.
I mean, I won't get it back until after I start.
No, I mean, and
But my expected class standard.
Which one did you show me which one I wrote it on?
well, I don't.
I thought it was just like a class standard.
Maybe you just pretended to write it. Because what we remember we talked about it.
Okay.
The problem was I incorrectly calculated.
Oh, might be.
Yeah.
Yeah, it's literally these, because it made this number.
Yeah, okay, now I remember.
And then you were like, but this it's fine. We'll call it a.
Just write done up here and hand it back to me. Done in person.
What is this blasphemy coming out of you?
You sack of crap, professor. How dare you?
I'm just gonna.
Don't put all that.
Yeah, I'm just gonna write it.
That's correct. I think that'll probably be better. Rob. Thank you. There he is. Oh, good. Grab. Here's 2 for Czar. These are for Czar. Not
Yeah,
bad.
just like, for some reason,
Cormac,
I created
yeah.
2y as, or derived at 2y. They're like, oh, no. Yeah.
2 for.
Same thing, same thing. Yeah, you got lost.
Nothing further to do. Is there ever, unless you've made a math joke about degrees and radians, that's the only time you do that?
What's that? Oh, that was our food.
Alrighty. Oh gosh, none of these are the right, none of this is the stuff for this class. None of it is. So, yeah, gosh. Oh, there's my Calc 3 notes, good. I already kind of know what's happening today. Keep track. So, oh, look at that. Done in poison, or person.
Poison. Yeah, that's fair. I'm pretty bad at writing.
I thought you were joking like in poison, just
No.
like being,
No.
but you wrote, yeah, I see it says person, it's pretty clear. Let's see, now that Ahmad's here, we can close the door. All right, so please, your job as always is to make sure that I recorded the score that you think you should have on that. And I think it's like if it says fix and resubmit, or if it says fix and I forgot to write resubmit, can you please get those to me like next week, next Monday tops? Sometimes stuff trickles in and it's becoming a real clusterfuck in my folder of things that are, not you guys, it's just my lack of organizational abilities, which are pretty sparse. So I took some time to like kind of think about what the rest of the semester is going to look like, because we have 3 weeks after this week. We literally have 4. Like, yeah, we would have 12 classes normally, just left because we're 3 times a week, but we don't have Good Friday class. And next Friday, I'm going to a math conference in Boulder. So I will record a lecture for that though. Like my plan includes that day. I gotta include that, but you won't have to be here.
What are you presenting?
I'm presenting myself, my beautiful self, and I'm just gonna go sit in on some talks. It's a student conference.
Oh, is it?
Yeah, and Mr. Cormac will be speaking.
Oh, he's a presentation?
Yes. Tell us the title of your presentation, because math titles, you know.
The walk sequences of polytrees.
Awesome. I don't know what that is, but I'll find out. I am super excited. It's cool. It's fun to go sit on a math. But and if you go to your profession, I highly recommend whatever your profession is, go to a conference.
Oh, these conferences are so fun.
yeah, okay, well, that's different than the math conferences there, but, like, generally, I don't know what's happening. I like go to, it's like, okay, this title, I kind of understand, and then I go, and then the talk, I don't understand at all.
I went to Dr. Gray's, like, his new on G-2 research, so his, like, presentations, I was like, yeah, I don't know.
Yeah,
I
and
was just watching it.
that's what they're like, and so you go, you sit, and it's fun, and you can see people watch. I was telling, who was I talking to about the conf with the math nerds like bashing into each other? Yeah, real analysis this morning. But like, it's just the math conferences are just filled with like lots of clueless people kind of bouncing into each other because they're just in their heads, right? They're just nerds, just walking, thinking about math, not able to function in the world. It's great. And there's cool books for sale. There's always like a shop, a store with cool stuff. Not that you can't buy all that same shit somewhere else. All right, so, oh yeah, so my plan was, the actual flow of this class does not include integration in vector spaces. So like but I want you to see that before we leave here. So line integrals through a vector field, because some of you will need that at some point. Physicists for sure are going to need that. So I want to make sure to at least have a day or two on that. So I kind of worked out a schedule, and I better get on it, I guess. So we're going to do some applications today. Applications of multiple integrals. Applications of double integrals just today. And then we are going to move into integrals in polar coordinates, which is, things start to get pretty fun there. And I'm hoping to at least introduce that today. That's my plan. I'm also thinking, how the hell are we gonna fit in the remaining like 7 skill checks or something? There's like 23 total. So probably, I'm sure you're gonna get some take-home skill checks. Is that gonna be a problem? It's just like freaking just
Gotta get the one anyways, let's go.
What's that?
Gotta get the one, have to retake it.
Yeah, exactly. So it'll be, we did do one take home, right? That, whatever that problem was, I don't even remember. But there was one. All right. Here is a lamina. What does that mean? What'd you say? What's that? Lamina. Yeah, lamina. What is, anybody know what that, yes?
I have no idea, but I'm guessing a surface.
There you go. That's the way. Yeah, that's how you do school. Yay! You know the word laminar.
I was
Maybe.
thinking of laminate.
Laminate, that's good. Like, yeah. And this looks like a flat thing, right? So it looks like a flat pool or something. And it was supposed to be uniformly thick. So this is a constant thickness sheet, but the density of the sheet changes depending on where you are. So sometimes it's more concentrated. It's all like kind of the same material. It's certainly all the same width. If this is an inch here, it's an inch everywhere around. But the density at a particular point, so if we coordinatize this and set up like some x, y coordinates on it, I could have a point in here, x, y, that's inside that surface. That point then represents its entire, all the way straight through. So it's homogeneous this way. In other words, the density doesn't change vertically or orthogonally to the surface. The density only changes in different locations here. Does that make sense, what I'm saying? That the thickness doesn't matter. This could just be a 2D flat thing, but doesn't seem very realistic. So, yeah, so the third dimension here is almost an artifact. We're mostly thinking in 2 dimensions. And so we've got this function rho of xy, which equals the density at point xy. And let's think about what this density might look like. It is going to be, I guess it would typically be a volume, but we'll just go with, we're gonna go with volume, I guess. So it's going to be some mass per volume, or it could be mass per area here. So let's look at something more specific. Let me get a little bit more specific here. Let's say I had, a sheet that's rectangular and kind of looks like this. And it's got some thickness to it. Don't worry about the thickness. The thickness is totally irrelevant in everything we're doing today. We'll get to 3 triple integrals and then we can have thickness. And things change in that way. But we got x, y, and let's say that maybe rho of xy is equal to x plus y. So let's just get some intuition for like what is this scenario that we have here. So our units of mass are, the gram, the kilogram, whatever. So let's just say kilograms there. And that is per cubic meter, I guess, square meter, sorry. So this is an area, or I could do kilograms per meter cubed. These are gonna be the same again because that thickness is irrelevant here. That thickness isn't going to change anything about the density. Is that confusing, what I'm saying there about that, or does that make sense? That you can just think of these as 2D or 3D, and it'll be the same for us. So what is up with this sheet? Where's it heaviest? Like if there was a force, a gravitational force, where's the heaviest part? Let's see here, let me give you some coordinates. There's 5 meters, there's 5 meters. What's that? 5, 5. It's gonna have the highest density up here, right? At 0.55, rho is 10. And so that's 10 kilograms per square meter, just at that one point. What would be the weight here if we had a gravitational force? 0. There's no mass here. So this thing starts off really light here. So this rho of 0, 0 is 0. Very light as you move this way. In fact, as you move along, x plus y equals a constant. So we could look at level curves for this thing. Where is the density constant? And it's going to be constant along these lines of perfect diagonals. So notice that like right across here, what do we got here? This would be 2.5, 2.5. And there, the rho there is 5. And that's also the density here, and that's the density here. So you've got these constant weight lines of constant density. And as you move out this way, they just become denser and denser and denser. So we have a vague idea what this weird surface is? Okay. Cool, cool, cool. So what if we want to find the mass of this thing? So how much total mass do we have there? I'm not talking weight, but what is the total mass given a density function that is changing throughout? So let's think about how we could solve this. So problem, find the mass of a lamina with density function rho of xy. So that's gonna be our problem. So let's actually start with a nice old rectangle, and we can kind of figure, we don't need no rectangle. Let's make something weird. Why not? So let's call that L for lamina, or lamina. I don't know how you say it. Anybody know enough to know if it's lamina or lamina?
Sounds like Levina.
Sounds like what?
Levina.
Labina? It does. It does sound like Labina. If only Labina was here with us right now.
She'd help us out.
She could take, yeah, yeah. She's feeling that right now somewhere. She's feeling the ears
She's
burning.
like looking over at our.
Yeah, yeah, kind of. So what we're gonna do is first off realize that if I do have a nice little rectangle of constant mass, so let's say I've got this rectangle, a little cut like this, and it's got width delta x and length delta y, like so. And I know that at some point, the density at, say, x sub I, y sub j, right here at this point, is a certain value k. I just know it's constant. And if this delta x and delta y are small enough, I can assume that that whole thing has roughly that density. So let's just make a little note here. If delta x and delta y are very small, the density is roughly constant on that little cube, our surface there. The density is approximately constant on this rectangle. Does that make sense? That if I know the density is 2.5 right here, and I draw a tiny little box around it, density's pretty dang close to 2.5 everywhere inside there. The smaller that rectangle or square gets, the more likely that's gonna be true. Is everybody cool with that? Because we're basically gonna write an integral. Because look what I'm doing, I'm thinking about a little cut up box and a representative point. So what we're gonna do is cut this thing up into little rectangles. So step one is cut L into M by N pieces, rectangular pieces. And then in each piece, grab a representative point, so that's gonna be x sub I, y sub j. 2, take representative point, and let's actually put a little star there, because I think that's the notation we've used, x sub I, y sub j, in each rectangle. Or how about this, in the I comma jth rectangle. 3, add up, well here, let's put the assumption, assume that rho is constant on each rectangle. And let's come up here, and this is gonna be step 4. Note that the mass of one rectangle, the mass of the ijth rectangle is what? So what's the mass of this little dude right here? Here, and we can take off that K there, because we can just use that as the reference. What's the mass of that piece? If we assume the thickness, let's assume the thickness is 1. So what are the units on density? Let's do physics the only way I can do it. Kilograms per meter cubed, so it's, or kilograms per meter squared, right? So it's mass per area. So this is mass per area. How do I get the mass out? Multiply by the area. So density times area. So is going to be rho of x sub I star, y sub j star, times, and here we could just put, we'll put delta x, delta y for a minute, but just notice that that is the tiny little area of the rectangle. And so this would just be, if we were working for that problem there, that would just be kilograms right now. Let me stop for a second. Let me know if that is making sense. This is kind of the heavy derivation for today. There's, well, that might be enough, but it's later. So I'm gonna add up all those kilograms. I'm basically going to take the density at each of these points, multiply by the area of the little square. That'll give me an approximation of the mass, and then add up all the masses, and that'll give me the whole mass. So 5, add up all these masses, and what we're gonna get is a double sum. Sum I equals 1 to m, sum j equals 1 to n. We don't know how many of those cuts there's gonna be in each direction, times rho of I star, x sub I star, y sub j star. And then here I'm gonna put delta A. And that could be delta x, delta y. And then I'm gonna let the number of cuts go to infinity. What does this turn into? What? Integral, that's the key word. There we go. That's kind of like what this whole thing is about, right? Integration. So when you see a Riemann sum, you know an integral is nearby. Just keep that. If you walk out of this class with nothing else, this is a good thing to know. Riemann sums mean an integral is nearby. So this turns into the double integral over the region, L, of the density function, rho of x, y, and then our area element might be dy, dx, might be dx, dy, might be something else if we're using a different coordinate system, and we will. So that's our formula. This is how you find the mass. So let's just put here mass equals that. So it's just doing a double integral. Given the density function that you don't have to come up with, someone gives it to you, or it's been determined experimentally or what have you. If it was done experimentally, you'd probably be doing this on a computer though. All right, let's come back to our example. Let's do this guy here. So call this L. You might want to go back and label that L in your notes. What is the mass of L? And so it's going to be integral over the x range, integral over the y range, density function, which was given to me, and then this could be, since these ranges are the same, it doesn't really matter, but let's just go like that. And as a nice way to get back into doing calc, could you work that integral out for me, please? And I'll be right back. Give you a few minutes of privacy. Totally recovered, Daniel?
Yeah. I think I just had allergy season pop.
Oh, is it? Oh, yeah.
Sneezing and coughing like crazy.
Yeah, my throat's been super scratchy.
Yeah.
Like at night, yeah. Cool, glad you're doing good. I'm not sure we've done a lot of these together, so I'm gonna show you my notation. First I do the y, so xy plus 1/2 y squared. And then we're gonna have, that's y, so y goes from 0 to y equals 5. Notice using that there kind of helps keep my brain straight because it's easy to mess that up. So I would recommend writing as much as possible. So now, see, look, that just looks like a standard integral, just that inner one at the evaluation stage. And then I'd evaluate that before I went on. So I put in the 5 for the y. So I've got 5x, put in the 5 here, 25 halves, parentheses, minus in parentheses, this was 0 in it. Now, here, that's just gonna be 0 plus 0, but just be careful. Use parentheses there. dx. Is there anything we need to talk about here so far? Let me know. Everybody's good, okay. So I'm just gonna rewrite this one more time. Integral 0 to 5, 5x plus 25 halves dx. And now, calc 1 time, that goes to 5 halves x squared plus 25 halves x. And that goes from 0 to 5. So, and now there's only x in there. You could write x here. Wouldn't be the worst practice, just to keep things straight. Practice making that notation. So put in the 5, put in the 0, everything's dead, so that's cool. Just gotta put in the 5, so I get 125 halves plus 125 halves. Cool, that's neat. So that is 250 halves or 125 kilograms. How many, did we get this? We got it, okay, cool. Questions if you didn't, anything? Yes, Brendan, yes, sir.
Why didn't we multiply by the area? Because isn't 125 our density?
No, so this is our density, and then this was the area.
Oh, okay.
Does that make sense?
Yeah.
Cool. Yes, sir.
Something for clarification.
Yes.
For integrals, you said that for derivatives, it's like it doesn't matter which way you do. You can do f of x, y, and also f of y x, and it'll be the same. Is that the same for integrals?
So.
Because I did this one backwards.
Yeah, you should have got the same thing, hopefully. Yeah, it wouldn't matter. It shouldn't matter. But if it does matter, that means you've probably screwed up something in the limits.
Oh, okay.
But I don't know if you remember, were you here on Friday?
No.
But surely you watched the recording where I did that example, where one way we couldn't do it with a certain order, but we could do it the other order. You might want to review that video.
I'll go over it.
Yeah, I think it'll actually be good for you to check it out, because it's an even more complete answer to your question. Other questions? Nobody, not after that. Nobody's going to ask anything after I asked. All right. Let's take this and make a very specific application. If the density is always 1, so if rho of xy is constantly 1, then what we get here, that the mass integral over our region L rho xy dA actually just gives us the area. Because think about how we broke this down. What we did was we cut things up into little area units like that, little rectangles, and we said, oh, the density times the area is what we're looking for. That gave us the mass. But notice that if the density is 1, what do I get? Just the area. So if we set the density to 1, we get the area of that strange shape, whatever it is. So area, this is another formula to remember. It looks exactly like what we had. How about I make this more? Area of L equals the double integral over L dA. There's just a 1, there's a secret 1 in there. So just make that little note here that there's a hidden 1 inside there. Now this thing that we had before was a square. The area of it was 25. That's not super exciting. So let's do something exciting. Something exciting. What? I hope I have something exciting here. Oh yeah, I made this guy up. Here's a good one. So let's have some fun. Let's practice some weird thinking, some sideways thinking. I was feeling really spicy when I made this one up, I tell you. And a lot of tea. You know, all that tea I bought, I got to drink it all, so I've been like freaking hopped up on tea like crazy. I can't believe I'm sleeping, honestly. All right, so X, Y. So my curves are going to be this. So L is bounded by X equals Y times 4 minus Y. You already know you're not liking that, maybe. And then X equals Y plus 4, Y equals 4, Y equals 0. No one likes these where X and Y are reversed from our normal way of thinking. But we can handle it. We got this. We can do this. And I wanted to do it so that we could think about how to make it not as stressful as it might be otherwise. Low-hanging fruit first. Y equals 4. Like it. So there's Y equals 4. Straight line all the way across. Y equals 0, aka the x-axis. Love it. So this is just the x-axis. Cool. Let me get different colors out so that this is actually more, bless you. I need other pen colors. Wish I could just get a box of the pink ones. That would be sweet. If anybody ever sees those, get it for me and I'll give you the money. You just point me in the right direction. Okay. I don't know if this purple is going to contrast. So here's one of our boundaries. Here's the other one of our boundaries. Anybody got any ideas on like how, maybe you have some cool ways to think about plotting that? So I'll just put it like this. What if I gave it to you like that? You'd probably be less stressed out. What is that shape?
Parabola.
It's a parabola. What are some points on the parabola?
0.
So when X is 0, Y is 0, yeah. What other thing gives me Y equals 0? 4. So on this one, I've got the points 0, 0, and I've got the points 4, 0, and I know it's a parabola. I could probably get the midway point when X is 2. What do I get out? 2 times 2, 4. So that would tell me which way the vertex is, right? The vertex is going to be right in the middle of those two zeros because of the symmetry of a parabola. So I'm just going to kind of do the same thing here. I'm going to know that this is a sideways parabola because the x's and y's are reversed. And so with that in my mind, now I can get in here and kind of make some sense out of it. But our parabola is going to have the points when y equals 0, x equals 0. So still 0, 0, just in a different order. And then if y equals 4, x is also equal to 0. So that's this point right here. You see how those? I got those 2 points right there. And now if I put in 2 for y, I get out 4 for x. So check it out. If I put in 2 for y, I get 2 times 4 minus 2. 2 times 2, 4. So the point 4, 2 are, 4, 2 is also on here. And then I know it's a parabola sideways. So now I just kind of wing it. And I say, okay, well, probably gonna go like that. That's actually a pretty good parabola. I'm pretty happy with it. Sometimes I make a graph and I'm even like patting myself. I was like, that's not bad. Sideways, not bad. So then I've got this other one. What's this one? Line, cool, linear, line, yeah, we know it's a line. How many points do you need to make a line? 2, so we just gotta get 2 points. So let's get some points. When when y is 0, x is 4. So that's one of the points on the line. So this is a line. And then when y is -4, x is 0. But I kind of want to like do positive ones over here. So what about when y is 4? Oh, that's good. Then I get x equals 8. So those are 3 different points. I just got to pick the good ones to make my line. So 4, 0 is here. And then 8, 4 is 1, 2, 3, 4 this way. And we go up. So that's 8, 4. And it's just a perfectly diagonal line. And so this is my thing that I want to deal with. Weird shape, cool shape. Not just length times width to get the area. So, gosh, let's just find the area of it. We know we could do the density, but it'll make the computation harder. So I want to give you a minute. Can you please set up the integral? Because I want you to practice this skill of setting up these integrals. So the area of L equals double integral over that region. You do dx dy or dy dx, your choice. But there's one choice that makes sense and one choice that leads to suffering. So I guess there's only one good choice here. And you got to think to yourself, which way are you going to make your slices, right? Which way are you going to slice this thing so that the left and the right endpoints, or the top and the bottom endpoints, don't change. They're all in the same curve, no matter where they're at. I didn't say that properly, but hopefully it kind of came through. Seeing some good slicing drawings moving on. So just a heads up, hopefully you're slicing on the horizontal. Yeah, otherwise life is pretty hellacious. So your cuts are horizontal for your strips. And then even once you get it set up, go ahead and work it out. What does it mean that my slices are horizontal? What will be on the outside, dy or dx? dy. Because we're slicing through different y values. So we want the outside integral, the outside integral always represents the axis where that references your slices. So slices referenced by the y coordinate. In other words, they're horizontal slices. If I had vertical slices, I'd have dx on the outside. That might be a good mnemonic device. So you're going to have dy dx. This is horizontal slices. And we're going to have this if we have vertical slices. Might be a good thing to just put in your notes. What do our slices run from to, the y slices? 0 to 4. So we start at y equals 0, slice all the way up to 4. You have to label this, and you have to think, and I'm going to give you a few more minutes to think on it, but your inner integral is going to start here and end here, but it's going to depend on y. So what is the start in terms of y? In other words, the x start in terms of y, and then what's the x end in terms of y? You don't have to look super far. You don't have to do any algebra to answer these questions. Was there somebody asking a question? Carmen, were you asking that? Where is this? For that particular y strip, what is the x coordinate of that left end?
Y times 4 minus y.
Right here, yeah, this formula. Just read it off the formula. This tells you the x coordinate. So this is just going to be y times 4 minus y. And then I'm pretty sure Daniel will also tell me that this one here is y plus 4. That's the right end point. So given the y coordinates, you can just grab the x's from these formulas. And then once you do that, your integral is going to look like this. Start to, what the heck is the end? 4, y plus 4? How does this feel? Do we have any questions about setting that up? Why don't we do it now? Let's do it. Let's work that sucker through and find the actual area. Pick your favorite units. What was that unit you had, Brandon?
Furlong.
Furlongs. Yeah, in furlongs. X is in furlongs. Y is in furlongs. Y is in cubit, X is in furlongs. Those are sweet socks, Daniel.
Oh, thank you.
Yeah, nice. Anybody want some tea? I got a lot. As Alexander and Eric know, I'll probably throw part of it away when I leave. So, yeah, part of it. No, I drink some of it.
75%.
Oh, there's Czar. You getting the cup out, Czar? Man, you're gonna like this stuff. This is a bug-bitten oolong. So like they harvest this, so like they let these certain bugs nibble on the leaves because it induces the leaves to release these terpenes, and adds a very unique flavor to it. There's no bugs in the tea, but it has been gnawed upon by bugs.
I think you mean there's not supposed to be any bugs.
That's it, yeah. I mean, no more than there is in anything else you eat. Give it a shot. I think you're gonna like that. What's that? Bug burgers? Yeah, assume anything that you eat at fast food is 50% bug.
That's why it's so cheap.
Exactly.
Something Japanese is like monkey.
It's not even cheap
I was gonna
anymore.
say, it's not even cheap.
Yeah, we're overpaying for bug burgers, I'll tell you that.
Unless you have reward points.
Well,
Yeah, they gotta get the app.
Get that.
They can sell your information, use my code. At least you get cheaper food though.
Use your code. SARS, bug burgers.
this first move might have been a little tricky. You might have been uncertain how to make it, but it's just a 1 and it goes to X. And then you're literally gonna take this equation minus this equation. And if this turns out negative, what happened? What do you think I did wrong if this turns out negative? I hear things. What do you think I did wrong, Calvin, if this turns out negative? This won't, but what if it did? What did I probably do wrong?
You took the wrong slices, like from right to left.
Yeah, exactly. Yeah, I probably reversed this left and right endpoints here if it turned out negative. Or I just totally did something terribly wrong, you know? So I'm gonna rewrite this thing completely so that it's just easier on my brain. And that's a negative 3y there. So let's see, so that's gonna go to 4y. This is negative 3y in net, so that goes to negative 3/2 y squared. And then 1/3 y cubed. Luckily, I got a 0 at the bottom. I'm gonna run this from 0 to 4, so now I just gotta put in 4, and I can do all of that math. Put in 4, you get 16 minus 48 halves plus 64 thirds. Now I don't wanna do anymore. Let's just get it all into a sixth. So that is 96 minus, oh God, what's 48 times 3? 144? Wow, that's cool, that's like 12 squared. And then plus 64.
Are you missing something?
Am I?
Did you put the 1/2 y squared in there?
The 3
You
halves?
have 3 terms and there's 4 before them.
Yeah, so these, I combined these two together.
Oh, okay.
That's where the -3 came from. Does that make sense?
Yeah, that makes sense.
Okay, awesome. Yeah, cool. No, thanks for keeping an eye on it. You never know with this guy.
You should double the 64. Cause you're changing 64 thirds to.
Oh, thank you. Yes, yeah, that one's, yeah, yes, thank you. Otherwise, yeah, it's gonna turn out kind of weird. So that's 128. Gosh, somebody help me out.
I got like 13.3 meetings.
Same.
13.3. So can we convert that to a fraction? I don't like
40 over 3.
40 over 3, thank you. That looks great. That does look like a 13.3. Cool. Furlong squared. Units squared. Cool. Does this make sense? Feels okay? This will probably be like one of the take-home things to work on. Probably should just start giving them to you while after. Yeah, actually, that's what I need to do. Start giving them to you right after we talk about them, so you can do them while it's still kind of fresh. Yeah, that's what I'll bring them in on Wednesday. Okay, is there any questions on that? Because that'll be like something you have to do. Yeah, I'm redoing some of the skill checks I was bequeathed from Cybert. So, I don't know, I'm just changing some things up. They're good stuff, but it's just not the way we're gonna go. All right, here's a problem, here's a conundrum. These are semicircle or quarter circles. So that is part of a circle of radius 1, that is part of a circle of radius 2. And this turns out to be the thing that I want to either find the density of or the area of. If this is x's and y's, what's the best slicing plan here? Let's try that. Let's try vertical. So if I do vertical slices, top and bottom well defined there, top and bottom well defined there, and then oh shit. Now I've got a different bottom. As I move across here, still same top. So what do you think? Should we do the other direction? Or is that the same problem?
Same problem.
Same problem. So I could do this with the systems that we have, but I'd have to break it into 2 separate integrals. So I'd have to break it into that one where I have that top minus that bottom, and then that top minus that bottom, or top and bottom, top and bottom. But we can do better than that. We can do a lot better than that. We can turn this into one integral that's actually so simple it's beyond belief. Like, these integrals are gonna suck. Just really quickly, because if this equation here, this equation would be square root of 4 minus x squared, and then this equation here would be square root of 1 minus x squared. And so just think about integrating this, something that looks like this. It's like arc signs and stuff like that in there. It's not good. It's tough. So what we're going to do is talk about a new coordinate system. There's a reason we've been writing dA. And it's not just because we don't know if it's dx, dy, or dy, dx. It might be in a completely different way to measure area. And that's what we're about to do, because we're going to start talking about polar coordinates. And I want to do a refresher. And we might not get to start the integration stuff today, but we're definitely going to do a refresher. Yeah, I think it's just refresher today. Hopefully it's a refresher. How many people have seen polar coordinates? How many have not seen polar coordinates? Okay. Okay, cool. All right, cool. So we're going to do a full glorious recap or first time through for you. So what is a coordinate? A coordinate is just, coordinates are ways to find things. They're directions. They're directions to a point. And what we're used to is hearing how far left or right do I go, and that's called the x-coordinate. How far up or down do I go, and that's called the y-coordinate. And I get a point coordinate, which is left, right directions, comma, up, down directions. And there's two pieces of information there. So one thing you could think of is that this is a two-dimensional space, and dimension, we talked about this in real analysis a little bit this morning, but dimension is the number of pieces of information needed, bless you, to locate something in a space. So for example, I'm in one dimension. If I am on a line, I only need to know how far this way of 0 am I, or how far this way. That's one dimension. In three-dimensional space, it takes 3 points, 3 pieces of information to find your way around. But the rectangular coordinates, the rectangular, aka Cartesian coordinates, aren't the only way. This is what we're used to. But there are way better ways to get around certain places. So for example, if you are driving a boat, right? If you have a boat and you're trying to steer somewhere, it's easier to tell someone, okay, facing north, go at this many degrees away from north and head this many miles in that direction. Does that make sense? Yeah? So that's the kind of coordinate system we're thinking about, and it comes down to simply the idea that this point here, P, could be located. If I say, this is standard direction, this is standard theta equals 0. So this means there's no rotation in this direction right here. And then I could say, okay, I'm the boat. How many degrees or radians do I have to turn my bearing so that I'm facing toward this thing? And then how far do I have to go in that direction? So polar coordinates are all about what angle of rotation do I take and how far do I head in that direction? And you can locate any point in the plane given that system. So let's actually talk about that. So we usually denote them as r theta. R theta equals the polar coordinates of point P. P. And since some of you haven't seen this, let's definitely warm up. Let's warm up to this idea for a while. And I think that's about all we'll do today. So for example, if I gave you this point, 4 comma pi over 2, take a minute, just take a minute, do this with me. Where is that point? Don't say it out loud, but work it out for yourself. Take this time to suffer through it. This is the direction I head out from the origin. This is how much I rotate. Do the rotation first, and then do the drive outwards. And it kind of helps to still have an X and a Y axis when you're thinking about them, because this would be theta equals 0. This is theta equals what? In radians. Thank you. Pi over 2, 90 degrees. This is theta equals. Oh God, it's going so slowly and quietly. Theta equals how much?
Pi over 2.
Thank you. Thank you. That was very forceful and confident. Excellent. And then what if I kept going? How many radians if I kept spinning? 2 pi. I'm back to 2 pi. It's the same as 0. Okay. So 2 pi, 4 pi, also negative 2 pi, negative 4 pi, infinitely many ways, depending on how many spins around I've done and whether I'm going clockwise. And for us, clockwise, or excuse me, counterclockwise is positive degree measure, positive angle measure. So what, can somebody give me, what is the rectangular coordinates of this point? So this is polar. What's the rectangular version?
0, 4.
0, 4. Do we see that? Okay. Rotate pi over 2 degrees, point you straight up, move 4 units in that direction. 2, 3, 4. You're at 0, 4. Let's do some more. What about, so I can actually have negative radii too, which is kind of a weird thing. A negative radius means, let me just quickly show you. If I give the point 4, or negative 4, comma pi over 2, people, sometimes you see this, especially in equations when you're graphing them. But this means face in this direction, but walk backwards from the origin. So this would actually be point to pi over 2, and then go backwards from that direction 4 units. So this point would be this, which is equivalent to what other measure? Can somebody give me, what is the positive degree measure for that one? Yes, what do you think, Kim?
4, 3 pi over 2.
4, 3 pi over 2. So there actually isn't a unique way to represent any point, because you could always just add multiples of 2 pi on. This point here is also add 2 pi onto that, and that's the same point. It's just an extra revolution around. How do you think I denote just this point? So if I have the rectangular point 0, 0, how could I show that in polar form?
0 and
Yeah, 0 and any angle. Don't move, but you can spin it at any angle. So the point 0, 0 would be 0 movement and any angle. That keeps me at 0. Rotate, but don't move. All right, let's get some more formality to this before we practice more. So let's do the change of coordinates. And these are formulas you're going to want to have at your disposal. So, you know, write them down or don't, whatever you see fit to do. Let's take a point P here, and let's say it's got XY coordinates, XY. So XY are its Cartesian coordinates, rectangular, but it's also got R theta as its polar coordinates. So point P is this, and it's also R theta. So we want the relationship between those two, so you got a formula. You don't have to wing it every single time. Anybody remember how to do trig? So what is x in terms of r and theta? Adjacent side. Yeah, what is it? R cos theta. Because the cosine of theta is the adjacent side over the hypotenuse. Yeah. So you give me polar coordinates, and I can convert it into rectangular using this formula, and then what's the y going to be? R sine theta. So this is to convert polar r theta to rectangular or Cartesian, xy. Let's go the other way now. If I give you the xy coordinates, let me help here with a little extra labeling. So that's y, that's x. What's r?
Square root of x squared plus y squared.
Thanks, Pythagoras, right? Good old Pythagorean theorem. So to go this other way, we know that r squared is x squared plus y squared. And for some reason, that's a good thing to know, i.e. r is square root of x squared plus y squared. But I would know both these because sometimes that r squared strangely shows up. And then, how do I find theta? Inverse something, yeah, I like it. Inverse what?
Sine or cosine.
Different. Try a different one. Sorry, those are close, related. Yes. Tangent. Yeah, we could do, we'd have to find r first to do that. So you're absolutely right. But tangent just, we know that the tangent of theta is opposite over adjacent. So it's arctan of y over x. So theta equals arctan, inverse tan of y over x. But you're right, Brandon, I just like to keep them without the r's in there, but you're totally right. I didn't mean to say you were wrong. I appreciate you, you're getting in there. Okay, so we got it. So, what if I gave you convert to rectangular? I'm going to give you a couple points. So these are polar. The polar form is going to be what I give you. And so we're going to have 2, 3 pi over 4. And 4 comma 11 pi over 11 pi over 6. And if you can do them exactly, like you can use your calculator, that's cool. There's probably even a polar to coordinate thing on your calculator. But if you can do these exactly, you know how many times my heart will swell? More than the Grinch's heart. Like that many more times. It's a lot.
That's funny if you wanted it large and small, like it's smaller.
Yeah.
Yeah. You get sad at us for doing this.
His heart shrunk 7 sizes that day.
His math students did the problem 9, his heart's shrunk 10 sizes.
No, you guys never make my heart sing. That's for my seminar. They're the ones that are here to crush my spirit. But I sure appreciate the people that are in there and give a shit. You can use those formulas. I always like just drawing them out. That's what I'm going to do. Alexander and I were just talking about this the other day. make sure we got a chance to come up with them. One of the things my seminar class folks, what they don't realize is I can tell who's been practicing meditation and not. Like in the end, it's just you can lie about it, right? I don't know what you're doing. They're supposed to keep journals. Well, it's pretty easy to fake a journal. I faked many a journal in my college career and high school career. Pretty easy to fake a journal. But you can't fake stillness. You either, like when we're sitting there and we do practice every day, and I hope maybe somebody's watching this from class who knows I'm talking about them. But you can just tell when people haven't been meditating. You just can tell. There's just a lot of fidgeting. Like you can't even sit for like 30 seconds without like tapping your feet or something, or scratching your face a lot. There's tells. All right, I'm gonna do this the old school way. So I just want the X and Y coordinates of this point right here, and I realize that if I drop perpendicular, I've got a nice 45 degree, or not, yeah, I do have a 45 degree triangle. Because this is pi over 4 right here, right? That's the difference between 3 pi over 4 and a full pi rotation. So that's a pi over 4. And I also know that 45 degree triangles look like this. If this is 1, 1, this is square root of 2. So I always keep that in my pocket, this special triangle. It's a good one to keep in your pocket in general. These are just ratios of the sides. So notice that this side is square root of 2 more than either of the other legs. What does that make these legs? So if 2 is square root of 2 more than these legs, what are these legs? Square root of 2. So that's just square root of 2, but that's a negative because it's on the negative x-axis, and square root of 2 is the positive. So this point here in polar is actually negative root 2, positive root 2 in rectangular, and you probably got negative 1.414 or something if you used a calculator, something like that, right? Did anybody get something different?
Which one?
This guy here.
Yeah.
Negative.
Yeah.
Okay, I wasn't sure what was going on. Are we cool on this one? Did anybody do it exactly?
I got it.
Yeah?
Yeah, I got square root of 2, but I used the decimal version.
That's cool. That's all good. What were you were saying something?
I just knew 1.414 was probably gonna be square root of 2.
Oh, so you saw the calculator and you're like, that's square root of 2. Nice. Oh, cool. Okay. That's good. Any other ways of doing this that you all did that? No? And I'm going to do this one the same way. So I got, once again, a special little triangle here. This is a pi over 6 short of 12 pi over 6. So, which would be a full 2 pi. So that's this guy here, good old 3060. That's the 30, that's the 60 right there, so that's 30, that's 60. And the way these guys work, the ratio of the sides is the shortest side is 1. It's opposite the tiniest angle. Next largest size is square root of 3. That's opposite the 60, and the hypotenuse is 2. And if you can just remember that side's 1 and that's 2, Pythagorean theorem can get you to that square root of 3 right there. So those are the ratios of the sides. Now the thing I've got has a length of 4 right here, which is actually twice this triangle. So it's really just this triangle multiplied, scaled out by a factor of 2. So instead of 2 here, I got another 2, and that's going to double this side. This is going to be 2 root 3, and this instead of 1 is going to be 2. And now I got to flip it, kind of work it around, but that means that the x-coordinate is going to be 2 root 3, and then I'm going down negative 2. So this is polar, and it's equivalent to 2 root 3, which would be like 3.4 or something like that on your calculator. Maybe you recognize those too. -2. Yes? Yeah? Anybody get it exact? Anybody else do it exact? Okay, awesome. And you didn't you didn't do it like you did with the calculator one where you saw the √2 and then recognized it. Did you actually?
No, I got 3.6 and I squared it.
That's all right. That's all right. That's cool. That's good finagling. All right. Any questions on this stuff, my friends? So let's end that today. I don't have a web work set up for you yet. Sorry. Was that a hiss? Someone hissing me for not having it?
Oh, no, I just did it.
Ooh.